starting off, I want to just talk about basic info about the exam. And as mentioned online, there are 2 parts. There is part 1 is 15 Mobius questions. And they're worth 2 marks each. So that equals 30. And that will be, you'll have 90 minutes. For that, you can only go forwards. And you have 1 attempt. So exactly the same as the midterm. Those questions will cover roughly like a sampling of the whole course. And there is a review quiz available. The review quiz is not for credit. You don't get any marks for doing it. It will show you a mark, but the mark doesn't count for anything. But you're welcome to try that up to 3 times before the assessment. It will close when the assessment starts. And just to get some practice answering 15 Mobius type questions within 90 minutes. Part 2 is, again, similar to the midterm. It's going to be 5 long answer questions. And 70 marks total. I'm not 100%, it doesn't matter how they're divided between the 5 questions, but the 70 marks total for that. So again, the sum of your thing out of 30 and your thing out of 70, that'll be taken out of 100 for your mark for the final. You will have 2.5 hours, which is 150 minutes to do that, plus 30 minutes to upload to CrowdMark. And don't forget, you do need to take a screen cap of each question. So again, same as the midterm, we're going to be much less forgiving now because you already know what to do, you've already done it. So again, my suggestion is when you open it up, go through all 5 questions, get all those screen caps right away, so that even if your computer goes down, that doesn't stop you from finishing those questions and submitting them to CrowdMark. So just that's my suggestion. You don't have to do that, but it's nice if you can just grab those screen caps right away so you know you don't forget, and then you'll have them just in case. When you get to the end, we'll give you a very large reminder. Don't close it, don't submit it until you've made sure that you've taken all those screen caps so that you have them when you're going to upload to CrowdMark. And again, the 150 minutes plus 30 minutes, CrowdMark is not going to enforce that, but we will. So we will know when you opened your Mobius and we'll know when you submitted your CrowdMark. And if those are more than 3 hours apart, 150 plus 30 minutes is 3 hours, that just don't be in that situation. Don't do that. You risk disqualifying your entire CrowdMark submission if you submit late. So don't do that. Make sure it's within that. I mean, if it's 1 minute late, well, it'll be okay, but don't miss that. So spend 150 minutes working on it and then make sure that you get it up to CrowdMark. It shouldn't take more than half an hour to upload. If you run into any technical problems, of course, do the same thing as in the midterm, either post on Piazza or email Divya. We'll be able to handle it. But normal circumstances, you should be able to get those in, no problem. There is in terms of the coverage, someone asked about that. It's everything in the course notes except Chapter 6, which is R, so there's no R on the midterm or on the final at all. There is nothing from 9.3, which is Markov chains, and there is nothing from 10.3. So somebody asked that, do we need chapter 10.3? No, you don't, as that is specifically excluded. Someone else saw another question. Does the review quiz help prepare for part 2 as well, or just part 1? Just part 1. There's already lots of sample exams that cover the part 2 material. So we've posted a sample final that together covers parts 1 and 2. So that's a great one to do. As well, there's the sample final in the course notes that again is split into like some short answer and multiple choice questions first, which is a good preparation for the Mobius part, and then some long answer questions, which is good preparation for part 2. And there's probably a few more on the MathSoc exam bank. Any kind of long answer question is a good indication of the kind of thing you would expect to see on part 2. And honestly, like what you saw in the midterm is a good indication of the type of question. So there'll be multiple parts. You'll have to do some calculations and possibly also maybe graph something or interpret something in words or justify why something makes sense in words, that kind of thing. So same as the midterm, you'll submit to CrowdMark, so your numerical answers and your process will be marked. So that even if you get the wrong numerical answer, if your process is right and your justifications are right, you can still get a good number of part marks. You can do the parts in either order, same as the midterm. You can have a break in between if you want one, that's fine. Oh, the one thing I forgot to say was when it is. It'll be available from 4 p.m. EDT on Tuesday, April 20th, and it must be submitted. Everything must be submitted by the same time the next day, 4 p.m. EDT, Wednesday, April 21st. So that means, right, if the part 2 takes 3 hours, to 2.5 hours to do it and 30 minutes to submit it, that means you want to start part 2 no later than 1 p.m. on Wednesday. So that's just keep that in mind. If you do part 2 second, then don't start part 2 any later than 1 p.m. On Wednesday. If you do part 1 second, then don't start part 1 any later than 2:30 p.m. I guess on Wednesday. And again, we don't expect it to take more than 2.5 hours total for the 2 parts. We're just giving you lots of extra time so that if you have any technical issues, then it should be okay. So we don't expect you to take more than 2.5 hours together for the 2 parts, but we're giving you extra time just in case you need it. I see another question. Is there a bonus question? No, there is not this time. There was one cool tricky thing on the midterm that we had on a question and we were trying to decide whether to cut it or make it a bonus, and we decided to make it a bonus, but so far that hasn't happened with the final assessment questions. There's nothing there that's too tricky outside of what we expect you to know that makes me feel like it should be a bonus. There are some parts that are a little bit tricky, but that's natural. There should be. But overall, if you've done well so far on the quizzes and you've understood the course material well and you're able to do those practice problems in the course notes, you should be okay with that. You should have plenty of time to finish this and do well on it. And that's what we want to see. All right. I see another question just sort of about like coverage related. Do we need to be able to derive moment generating functions for all the distributions? We would be unlikely to ask you to derive something that is exactly in the notes because it is open book. So maybe I'll mention that as well. So you are allowed to access anything on Learn or Piazza, basically. I was about to write pizza. I'm so close. Every time I type Piazza, I want to type pizza, but I almost just wrote it. So anything on Learn or Piazza, you can go back and see other things. But it has to be your own work, and you're not allowed to just Google things. So it must be your own work. And if you do have a question or run into a technical difficulty or anything, the instructors will be watching Piazza fairly closely. And so if you have a question, it's kind of similar to if you were literally in the exam room and you had a question, you could raise your hand. Same kind of thing. You can make a private post on Piazza, and one of the instructors will be watching, not in the middle of the night, but we've got a pretty good schedule of covering. So we should be, if you run into interesting problems, then just post on Piazza. So I'll add that too. Can make a private post on Piazza if you have a question. All right. I saw another. Are we expected to derive similar results to the proofs in notes? Okay, that's a great question. I think that also relates to the other one with moment generating functions. So again, we probably would not ask you to derive something where the proof is already literally written in the notes and you could just copy out, but we absolutely could ask you to derive something similar. So that could be using similar techniques. So it's possible. I'm not saying we will or will not. So let me see, possible to ask for derivations or proofs or whatever. It's not going to be a large focus, honestly, because as that user says, most quizzes and problems have been computational so far, so it's probably going to stick mostly to that. But there could be a question, a part of a question that includes some kind of derivation or proof. So like, for example, to like derive the probability density function of some transformation of a random variable, like show it's equal to something, or to use those summation results to prove something about an expected value of a new random variable that you haven't seen before. So again, thanks for both of you who asked that question. That's something that you should be expected to do, but it won't be super complicated, and it will use similar techniques to the proofs that you have seen in the course notes. I see another question. Will the Piazza participation marks be up soon? They'll be up on Monday. I think I said that. I can't remember if I did, but they'll be up on Monday. So any participation that you do on Piazza between now and Monday, like over the weekend, hopefully you're studying a little bit for this exam. If you have any questions, then you can post on Piazza and get credit basically for those questions. So yes, we will post those participation marks on Monday. Is the sample final answers available? Yes, they are right there in the description of the document. So if you look at the sample final, there's a description of the document. It has all of the numerical answers. Solutions, no, because reading solutions is not an effective way to learn. Reading solutions robs you of the most important part of answering a question, which is figuring out what the first step is. And reading a solution takes that away from you. So the numerical answers are all there. It's possible that one of them is rounded incorrectly if you used a slightly different, like if you rounded at different points. But it should be okay. And if you have any trouble, if you can't get to the same answer that I'm given, then you can post on Piazza and someone will answer. Someone also mentioned, MathSoc exam banks. I mentioned those before. Maybe you weren't here yet. But yes, all the exams on the MathSoc exam bank are a great idea to use as preparation. They do go back a while. But I mean, stats is pretty much the same. There haven't been any revolutionary discoveries in Stat 230 material in the last 10 years. So yes, you can absolutely use those as a resource as well. And what I would recommend is don't just do a zillion different practice problems. I would start by like figuring out what you know well. So maybe like try one practice exam, see how it goes. And if you do really well on some topics, then you don't need to study those things more. If you already have a good handle on something, you don't want to waste your time preparing for something that you're already good at. You want to focus your time on the areas where you're weakest, where you need the most improvement. And that sucks. Like, it feels no good to do something that you're bad at, but that's how you get better. That's how you'll get better at it and how you'll be more prepared. Another question, someone says, is there a bias on post-midterm content? Yes, it says that on the information. The post-midterm content is more highly weighted. The sample, it does cover the entire course, so it covers everything, with a slight bias towards the material since the midterm. Same as all the sample finals, right? All of the sample finals you will ever find are going to cover the entire course with a slightly more weight on the post-midterm material. Again, it's basically exactly the same process as the midterm. The only difference is you have 5 questions instead of 3 on the part 2, and we give you more time for it. But everything else in terms of the process for doing it is exactly the same as the midterm. And since you all managed to do that, you should be okay. Oh, I see two people questioning. The final is a must pass, correct? Do we need 50% on the final to pass the course? Yes, according to the course outline, you do need a 50 on the final. So whether that's 30 out of 30 on the Mobius and 20 out of 70 on the long answer, or other things like that. I'm going to move over here and get going with specific questions. Okay, so the first question was, where did it go? Oh, can we go through question 6C and question 6E of the sample final? We absolutely can. So basically we have X and Y are independent. X is normal 3, 4, and Y is normal -8, 25, and they are independent. And then u is equal to x minus 5y, and v is equal to negative 6x plus c times y. And then the questions, I want to focus on C and E just to answer your questions, but part A is to find the distributions of U and V. And so you know that if these U and V are linear combinations of independent normal random variables, they are going to be normal as well. And you can find the means and variances of U and V. Maybe I will write them down. So U is going to be normal because, again, a linear combination of independent normals is normal, with mean equal to the mean of x minus 5 times the mean of y. Well, that's going to be 3 minus 5 times negative 8. And I'll fill that out later. Variance equal to the variance of x plus negative 5 squared times the variance of y plus 2 times the covariance, but there is no covariance because they're independent. And so that's going to be, well, the variance of x is 4, and then plus negative 5 squared times 25. And that I will check on my calculator because I can't do that in my head. Sorry, I'm sure someone could be faster than me. So 3 minus 5 times negative 8 is 3 plus 40, so that's 43, I think. And then 4 plus 25 times 25. Okay, I'm not convinced that was right. 25 times 25 is 625, and then plus 4 is 629. Okay, cool. Fabulous, thank you for confirming. And then similarly, V is going to be normal with mean negative 6 times the mean of x, so negative 6 times the mean of x, which is 3, plus C times y, so that's C times negative 8. And then the variance similarly will be negative 6 squared. So that's positive 36 times the variance of x plus c squared times the variance of y. And so that we can't really simplify much other than to say that it's, I guess, 18 minus 8c. And the variance is 36 times 4, 144. Oh, hey, that's a nice number. 144 plus 25c squared. So we can't get rid of the c yet because we don't know it. For B, we want to find the value of B such that the probability that U is less than B is 0.975. I'm going to skip that because nobody asked about it. But that's something that you can find using the normal tables. You take your normal, subtract the mean, divide by the standard deviation, and then you have a standard normal, and then you can look up the appropriate percentile in the normal table. And in this case, it's looking for the 97.5th percentile, and so you can solve for that. Next, part C was the one that was asked about, was to compute the covariance of U and V. So I'm going to skip B unless there's a clamor for me to do it, but C is to find the covariance. And there's actually 2 ways that you can do this. I'm going to do it the easy way, which is the way that we hope you would do it, but I'll tell you about the hard way as well, but I'll start with the easy way. So the covariance of U and V is just, well, we can sub in the definitions. This is the covariance of x minus 5y with v is negative 6x plus cy. And so we can use the rules for covariances of linear combinations. It's basically exactly the same way that you would multiply 2 like polynomials with 2 terms in it together. If you've ever heard the acronym FOIL, you go first, outside, inside, last. If you've never heard that, now you have heard a thing. So you exactly do that. You basically say this is going to be the covariance of the first 2 things. So x with negative 6x. Well, any constant we can just pull outside. So this is going to be negative 6 times the covariance of x with x. And then outside, so x with cy is going to be c times the covariance of x with y. Inside, so negative 5y with negative 6x, the negatives are going to cancel out, and we'll have 30 covariance of y with x, pardon me. And then finally, last. So negative 5 and negative 5y and cy is going to be negative 5. So that'll be minus 5c times the covariance of y with y. So looking at that, it looks like we made it worse. It's like, no, we made it worse. But remember two things. In this example, we were told that x and y were independent. So that means this is 0 and that is 0. The covariances are 0 between x and y because we were told that x and y were independent. And independence does imply 0 covariance. So we can just get rid of that. And then the other thing to remember is that the covariance of a variable with itself, by definition, that's just the variance of that random variable. So really, this is negative 6 times, oh, thanks. Yeah, it worked out. Negative 6 times the variance of x. And the variance of x was, I believe, 4. And then minus 5c times the variance of y. And the variance of y was, I believe, 25. Yes. So minus 5c times 25. And so I guess we can put that all together if we really want. We get, they're both negative, so whatever, negative 24 minus 125c. Hooray, cool, we have a covariance. And you might be concerned that, oh no, this looks like it's always going to be negative. I guess unless c is extremely large and negative. But that's okay. Remember, covariances are allowed to be negative. Variances cannot be, but covariances, no problem. Covariances are allowed to be negative. So we end up here with this negative expression, negative 24 minus 125c, which represents the covariance of u and v. So that's the way that we expected people to do it, to use this linear combinations of those variables. Oh yeah, I totally forgot about the covariance of x and y equaling 0. Exactly, that was one of the tricks that makes this easy. Yeah. So then, yeah, I think part D asks what value of c makes these values uncorrelated, and exactly, yes. So if we set c equal to negative 24 over 125, then that will force the covariance to be equal to 0. But interestingly, it does not make u and v independent. It just makes them uncorrelated. So unless they were like jointly normally distributed, then we could conclude independence. But just because they have 0 covariance in general does not mean that they have that they're truly independent. But yeah, that's all you would need to do. So that's how you do C. The other way to do it, by the way, if you sort of forgot this rule, I'm going to just mention this. Like we could calculate, we already have E of U and we have E of V. So we could calculate E of U times V, and we could sub in, that's going to be the expected value of x minus 5y times minus 6x plus cy. And then cross multiply those two binomial expressions, pull out the constants, separate it out, and use the fact that since x and y are independent, that E of xy is equal to E of x times E of y. So you could do that, but you don't need to. It ends up being a bit harder. Oh, someone asked what rule, where is this rule? It's on page 223 of the course notes. I did not memorize that. I just had to look it up earlier when someone asked about it on Piazza. So this rule here, I think, is what you're referring to. It's in, I think it's section 9.5 in the course notes, rules for means and variances of linear combinations. So it's page 223. Again, I did not memorize the course notes. I just happened to have looked that up earlier today. So I do know where that comes from pretty quickly. All right. I will look at part C, or part E then, which was also asked about here. Because again, D is just finding the value of C that makes these uncorrelated. And part E is the fun part. So this is saying, now we have a bunch of W's. So we have W, I guess, equal, lies. W1 through W100 be an unknown continuous distribution with mean 2 and variance 9. So I'll just say mean 2, variance 9. And we're going to assume that xi's are independently distributed normal 3/4. So x1 through x100 our normal 3/4. So like the same x's from the beginning of this problem. And we're assuming that the xi's are independent, these are independent, the w's are independent of each other, the x's are independent of each other, and the x's are independent of the w's. That's another assumption, so independent as well. So each set of w's are independent, the x's are independent, and they're cross-independent as well. And now we're going to use a suitable approximation to compute a big, ugly expression. I'm going to write it down, and then we'll try and figure out how on earth to do this. So find, or rather approximate, the probability of 1 over 100, the sum as I goes from 1 up to 100, of 2wi minus 3xi plus 6. So the sum of all of that is greater than 0.5. And it's really easy to look at this expression and just be like, what? How can I possibly do this? But the key here is it says use a suitable approximation. So you want to think about what approximation can you use when you are taking a large number of identical and independent random variables and either taking a sum or average of them. The thing that we want to use is the good old central limit theorem, which I know is like the last thing we learned in the course, but it's going to come up a bunch because it's really important and super interesting. So we want to find the probability of basically the sample mean, the average of 100 of these variables here. So what we can do is think about one of these variables. Let's just think about one of them. We could call it yi. Like, let's do that. Let's let this equal yi. We know that yi is not necessarily a normal random variable, right? It's equal to 3 times the normal random variable, or negative 3 times the normal random variable, but also plus 2 times this w, which we have no idea what distribution it is. It's just some random continuous distribution, and then plus 6. So we don't know the distribution of yi. But that's okay. For the central limit theorem to apply, we don't actually need to know the distribution. We just need to know the mean and the variance. And so we can see if we can do that. Let's find the mean and variance of one of these yi's, and then we can use the central limit theorem because all of these yi's are going to be identically distributed and independent from each other. And we're taking the average of 100 of them. Then we can use our central limit theorem. So we let yi equal 2wi minus 3xi plus 6. And we can find the mean of yi, any one of them. Again, using linearity, it's going to be 2 times the mean of w, which is 2, minus 3 times the mean of x, which is 3, and then plus 6. So that's 4 minus 6 plus 6, which is 4, I think. Have someone correct me if I'm wrong. And similarly, the variance of yi, well, this is going to be 2 squared times the variance of wi. Variance of wi is 9. Plus negative 3 squared times the variance of x, which was 4. And then the constant, adding 6, doesn't change the variance at all. Remember, so shifting a variable by a fixed amount doesn't change the spread. So the 6 has nothing to do in terms of the variance. Then we would also have, I guess, 2 times negative 3 times, or 2 times 2 times negative 3 times the covariance between wi and xi, but they are independent. So there's no covariance to worry about. We just have this. And so we don't have to worry about the covariance, and we don't have to worry about the plus 6, because again, shifting a distribution by a fixed amount doesn't change how spread out it is around the mean. So we have 2 squared times 9 plus negative 3 squared, which of course negative 3 squared is positive 9. Actually, so 9 times 4 plus 9 times 4. So 9 times 4 times 2, 72. I should have been able to do that in my head, sorry. Okay, so now we have the distribution of each yi, and what we are looking for is the probability that y bar is greater than 0.5, where y bar is just equal to this, like sum of the yi's over 100, right? The average yi. And so we can use the central limit theorem. Y bar is going to have a distribution as follows. So since we have 100 of them, not 100 specifically, but a large number of IID, that stands for independent and identically distributed random variables, the central limit theorem tells us that y bar is approximately, so it's not exactly, but it's approximately normal, with mean equal to the mean of y, which is 4, and variance equal to the variance of y, but then divided by n, divided by the number of them that we're adding up. So 72 divided by 100. So this is one of the good old central limit theorem ideas. So the central limit theorem tells us if we have a bunch of IID random variables, we can approximate the sum of them by a normal with mean n times mu and variance n times sigma squared. Or we can approximate the sample mean, which is taking them all, adding them up, and dividing them by how many there are. It's normal with mean mu and variance sigma squared divided by n. Someone just commented, I thought it was by the square root of n. No, the standard deviation would be the square root, right? That's the variance is sigma squared over n. The standard deviation would be sigma over root n. So good intuition. The square root is going to be involved, but it doesn't come yet. Yeah. Okay, so with this in mind, we have the approximate distribution here, and we want to calculate this. So now it's just become a normal distribution kind of question. So the probability that y bar is greater than 0.5 is, again, approximately equal, using this normal approximation, to the probability that y bar minus the mean divided by the standard deviation, which is going to be the square root of 72 over 100, is greater than 0.5 minus 4 divided by the square root of 72 over 100. You know what I did? I took 3 times 3 and got 6. 3 times 3 is 9, folks. Oh my god. Okay. Woo, yay. So yes, make sure you check your math. So yeah, that was me just trying to do math too quickly and getting that 3 times 3 is 6, not 9. So let me go back and fix this. So this 3 here is still a 3, but that means this is a 1. The rest of it's fine. The rest of that's fine. This is a 1 as well. And then that means this is a 1 and this is a 1. Okay. Thank you for catching. Yes. Thank you. 4 minus 9 plus 6 is 1, not 4. I can't math today. Okay, cool. Got it. So now with that in mind, with the correct expression, we end up with 0.5 minus 1, all divided by the square root of 0.72. That's just the probability that a standard normal is greater than negative 0.58926. Or we can round that to negative 0.59. And now here is where you would go look up that value in a normal table. So of course, like what I would do instantly is just sketch myself a little normal curve. If that's 0, if we want the probability z is greater than negative 0.59, so here's negative 0.59, we want the probability it's greater than that. So that's just going to be equal to the probability that a standard normal is less than positive 0.59 by symmetry. And then you can look that value up in the normal table, and there you go. Question. By the way, are we allowed to use calculators on the final exam? Calculators, yes. I mean, you shouldn't need R or any heavy lifting. You really, really shouldn't. Everything will be doable with just a normal table. You could use the normal tables that we've given you, like that are in the course notes or in the formula sheet, or you could use like a normal calculator. That would be fine. We would accept either. But remember, we're not just looking at your final answer. We're looking at your process. So if you wrote this and then equals a number, you would not get all the marks because you need to show your work. So you have to do the work anyway. Oh, for Mobius. Yeah, for the Mobius questions, there's an online normal calculator. If you want to use that, that's fine. Sorry, I apologize for being confusing there. Yes, there is a Mobius online normal calculator that is allowed. Oh, I see another question. Do we have to use the continuity correction when approximating discrete random variable with CLT when possible? And if we don't, will we lose marks on the exam? Great question. So the continuity correction is useful in improving the accuracy of a normal approximation when, if and only if, you're using the normal approximation to approximate a discrete random variable. So for example, in this one here that I've just done, you would not need to use it because x was a normal random variable, which is continuous, and you were told that w was also a continuous random variable. So x 3w minus 2w minus 3x plus 6 is definitely a continuous random variable. So that's why here we do not apply a continuity correction. For if it was a different situation where you are approximating a discrete variable with a continuous one, it is usually the right idea to use a continuity correction. If you forgot, I mean, maybe you'd lose half a mark. Honestly, it wouldn't be a huge deal. So just err on the side of using it if you should, because it's not hard to do and it does improve the accuracy. So again, you only use it, maybe I will write this down, continuity corrections. You're going to use it when you're approximating a discrete distribution by a continuous one. So for example, the normal approximation to the binomial or to the Poisson or to any discrete distribution. And you would not need it if you were using like say the Poisson approximation to the binomial, because those are both discrete. You wouldn't need it if you were using a normal approximation to a sum of exponentials, because they're both continuous. Can we do an example on continuity correction? Sure. Do you, person on Piazza there, do you have an example, like something from the course notes that you want to look at in particular that was troublesome, or do you want me to sort of make one up? I'd be happy to do that. I could make up a quick example, but whatever you think. I'll give you a second to respond. I know it's not easy to reply instantly to a question like that. But yes, I can definitely do an example of a continuity correction. Don't have one in mind. No problem. Yeah, I'll just make one up. So let's do another example. So I'm gonna just draw here a distribution. I'm gonna try and let's make it a binomial distribution. Nice, here we go. Binomial distribution. Try and make it look relatively symmetric. And okay. 1, 2, 3, 4, 5, 6, 7. So this is a binomial. 0, 1, 2, 3, 4, 5, 6. And we'll say this is a binomial with 6 and 0.5. So I made this up. It doesn't look quite like this, but that's the idea. So if we are doing a normal approximation to this, which would be a really bad approximation actually, like a normal approximation 6 is not really big enough to do for the central limit theorem to apply, but just imagine we were, then we would basically think about overlaying a normal distribution over top of this histogram. So we would basically be doing this, like that. Okay, sweet, pretty good. So this is going to be approximately normal with mean. Now we know the mean of the binomial is the product of the parameters, so 6 times 0.5, which is 3. And the variance would be 6 times 0.5 times 1 minus 0.5. So 6 times 0.5 times 0.5, which is 3 times 0.5, which is 1.5. So 1.5 is the variance. So that's what our approximation is doing. So if we wanted, say, the probability that x is greater than or equal to 4, what we would want to approximate, right, if we just took the probability that a normal 1.5 was greater than or equal to 4, that would basically be going like from here and taking the area underneath this curve. That's what that would be doing. And we can see that that's not quite right. Like if we want the probability x is greater than or equal to 4, we really want to sort of include this part of this bar here, right? We really want like a better approximation would be all of the 4 bar, all of the 5 bar, and all of the 6 bar. So this point here on the x-axis is like halfway between 3 and 4. So what we would really want is for this to just be equal to, again, approximately equal to the probability that this normal is greater than 3.5. And then we would use this normal approximation. So this is going to be the probability that x minus 3 over the square root of 1.5 is greater than 3.5 minus 3 over the square root of 1.5, et cetera, et cetera, et cetera. So we would keep going from there. So again, because we want x greater than or equal to 4, what we really want is all of the area underneath the curve from here and up, rather than from here and up. That's what the continuity correction is doing. Similarly, if we wanted the probability that x is less than or equal to 1, I don't know, why not? Then we would go, right, if we want less than or equal to 1, that would go to here, but we really want to go to here. So we would take that as the probability x is less than 1.5. So we're going up by half, like up halfway to the distance to the next value to incorporate the entire area that we want to integrate over. So you could see the same kind of thing, like if we wanted probability that x is between 1 and 4, something like that. Oh no, that's stupid. That's just the other one minus the other two. But let me get a better example. Whatever. 5. Sure. This would be the probability of x going. So if we want to exclude the 1 bar, we would go from 1.5. And we want to exclude the 5 bar, we would go up to 4.5. But if we wanted to include the 5 bar, we would go up to 5.5. Right? That's the idea. If we want to include it, we go past it and include it. If we don't want to go the other way. Oh, if it was just strictly less than 1, would you go less than 0.5? Exactly. Yes. So whether you go up or down, I hesitate to sort of like make a formula for it. You just kind of think about like, do we want to include this bar or do we want to exclude this bar? And if we want to include it, we go halfway to the next value on the side where we include it. And if we want to exclude, we go halfway to the next value on the way in the direction that we exclude it. But remember, this here example, we knew that all of the integers were potential values. If we had a variable where it only existed in multiples of 10, we would want to go again halfway to the next value. So we would want to go up or down by 5, not by 0.5. So it's always halfway to the next value. If you had a variable that was only taking even values, you would go plus or minus 1 to use that continuity correction. So it's not always 0.5. It usually is, because we're usually dealing with integer valued random variables. But if your variable can only take multiples of 2 or 10 or 5 or whatever, then you're going halfway to the next value. That's sort of the logic behind the continuity correction. Hopefully this picture kind of helps a little bit. Person who asked that question, is that okay? Oh, how did I get normal 3, 1.5 again? Yeah, no problem. I'm going to just scroll down here. Because x was binomial, the mean is 6 times 0.5 because it's NP. And the variance of a binomial is 6 times p times 1 minus p. So that's where those came from, because we had a binomial to start with. So hopefully that makes sense. And thanks for asking the question. Again, they're not a huge deal, continuity corrections, but they do help with the accuracy of when you're approximating a discrete distribution by a continuous one. I sometimes have trouble distinguishing between whether to answer a question using the Poisson process or exponential. Any tips on how to tell which one to use when? Fabulous question. So let me scroll down a bit more here. Get rid of this normal question. Poisson versus Exponential. The new film by Michael Bay. No. I'd watch that. I don't know. The great question. So they're both very closely related to each other. We know that a Poisson is counting up the number of events in a Poisson process over a fixed time. or space, whatever, a fixed interval. Whereas the exponential is the waiting time until the next event. In a Poisson process. So they both are very linked to each other. In fact, there is a discrete analog of both of these distributions. If we think about this in the discrete case, counting up the number of successes in a fixed number of trials, that's a binomial. Waiting until we see the next success is a geometric. So the Poisson and exponential share the exact same relationship as the binomial and the geometric. Isn't that kind of neat? But that's the key difference between them. So if you're looking for, how long does it take until this happens, you want an exponential. If you're looking for how many things happen in this interval, you want a Poisson. But the cool thing is you can often switch between them. And I want to give you an example. Let's say I wanted to find the probability that the waiting time to the next event, let's say next bus. Buses don't actually follow a Poisson process, by the way. They follow a schedule, even if sometimes they're off it. It's not really truly a Poisson process. But for the waiting time to the next bus is greater than 10 minutes when buses come on average the 3 per hour. Okay, so here's a question. We could do this in two different ways. We could write this as a Poisson problem, or we could write this as an exponential problem. In both cases, let's turn everything into minutes. So 3 times an hour, that means the rate is how many buses per minute. That's going to be 3 over 60. What's that? 1 over 20? 0.05? Hold on. Calculator, save me. 3 over 60? Yes, 0.05. So that's our rate of buses per minute, basically, for our Poisson process. And so we could let x equal the number of buses in 10 minutes. And then x, we know, is Poisson, because we're counting up the number of buses in a Poisson process in a fixed amount of time. So that's going to be, lambda, which is 0.05, times t, which is 10 minutes. So 0.05 times 10, which is 0.5. So that's our distribution. And in this case, if we want to know that the probability that the waiting time to the next bus is at least 10 minutes, what does that tell us about the number of buses that arrive in 10 minutes? It's kind of hard to ask questions when you're not here in front of me, but if we want the waiting time to be greater than 10 minutes, then the number that we see in 10 minutes has to be 0. So we want the probability that x is equal to 0. And so we can plug in the definition of the Poisson random variable. It'll be e to the negative 0.5, 0.5 to the 0 over 0 factorial, which is whatever it is. I don't even care. Or a totally different way of doing it, we could let, say, y equal the time until the next bus. And we know that y is going to be exponential because this is a Poisson process, and the time until the next bus is exponential. With parameter, theta is 1 over lambda, right? So our theta is 1 over 0.05 or 20, right? Because theta equals 1 over lambda, and lambda here is 0.05. And we want, in this case, if we want the probability that the waiting time to the next bus is greater than 10 minutes, this is a little bit more obvious. We want the probability that y is greater than 10 minutes. And so for that, we can use, well, it's 1 minus the CDF of this exponential distribution. And the CDF of the exponential distribution is 1 minus e to the power of negative t over theta. So negative 10 over 20. Well, guess what? This is equal to e to the negative 0.5. This is equal to e to the negative 0.5. So they're equal to each other. So both of these ways of approaching this problem will get you the same result. And so you can usually rephrase any problem about the Poisson process, maybe not any, but most simple problems about the Poisson process, into an equivalent problem about an exponential random variable, and vice versa. So honestly, you could just sort of use whichever one you're more comfortable with. I would recommend sort of getting comfortable with both so that you have both implements in your toolbox. But you can see that it wasn't particularly harder one way or the other. It's still sort of the same amount of steps. This second one here maybe feels a little bit more natural the way that the question was worded, because we're saying like, what's the probability that the waiting time is greater than 10 minutes? So we already sort of have the waiting time as like an implied variable that we're interested in. But we can always rephrase that, right? The waiting time for something being greater than t is just saying that in an interval of length t, no events occur. And we could use it, and we could do it with a Poisson random variable, or we could do it with an exponential, and we would get the same result either way. So, person who asked that on Piazza, does that make sense? Oh, can you walk us through how we would approach questions that ask for time between events? They're exactly the same, right? The Poisson process is memoryless, it's independent. So once an event has occurred, it's like time is starting all over again. So anything dealing with the time between events is exactly the same as the time until the next event. It's a really cool thing about that exponential distribution is that it's memoryless. So just because we just got an event, that doesn't change anything. Like nothing that happened before now matters at all in terms of an exponential. So whether it was time between events or time until the first event or time until the next event, all of those are the same. They're all modeled by the exponential distribution. And we also go through why for part A, question 8 on the sample exam from the course notes, option C is true. Yes, we can. Okay, so let's think about these statements. Are they true or false? E of y is less than e of x. Well, we can see that e of x is looking like it's centered around 1, whereas e of y is like spread out more, right? Like it's looks like it's above 2, a bit closer. It's not quite symmetric, but like certainly the average is higher, because like the average, you can think about a mean as like the balance point. If this was a physical object, where would you have to place your finger to make it balance? And for x, it's clearly somewhere around here, and for y, it's somewhere maybe around there. So definitely that is false. So nope, that's not true, because e of y is actually bigger than e of x. Oh, I'm sorry. I realized I copied it down wrong. It was supposed to be this way, which means the answer is yes. Sorry about that. Everything I said is still true, but I copied it down wrong. So yes, definitely e of y is bigger than e of x because y is centered a bit further out than x is. E of x equals 1. Well, here in the graph, that mine is pretty badly drawn, but in the graph you can tell that it's a symmetric distribution. So it's symmetric around the point 1, and therefore the mean is definitely 1. So yes, by symmetry, that's definitely true. You asked why option C is true. So I'm going to skip it. I'm going to come back to C last. So standard deviation of x is greater than the standard deviation of y. Well, x here, standard deviation, right, measures how spread out things are around the mean. And very clearly from looking at these two graphs, instantly, without any calculations, you can tell that this y is more spread out around its mean than x. X is pretty concentrated, and y is pretty spread out. So that's definitely false. Clearly, the standard deviation of y is wider than the standard deviation of x. Lastly, the variance of x is less than or equal to 1. This is something that requires maybe a little bit more thought, because the variance is the average squared distance from the mean. Well, the furthest, we know the mean is at 1, and the furthest you could possibly be from the mean is 1 in either direction, right? We could be 1 away this way or 1 away this way, but most of the time we'll be less than 1 away. And the variance is a weighted average of the squared distances from the mean. So the weighted average of a bunch of things that are less than 1 is going to be less than or equal to 1 as well. So I'm going to say yes, since there is average squared distance from the mean. And in here we can see that the maximum distance from the mean is 1. And so the average is going to be less than that. So then let's go back to here. Why is C true? The probability x equals 1 and the probability y equals 1. If we look at the height here of this function, we can see that that's definitely different, right? But remember, the PDF curve is not the same thing as the probability that x equals or y equals any particular value. For a continuous random variable, which both of these are, the probability that the variable equals any value is always 0. So it's yes, because they're both equal to 0. The probability any continuous random variable equals any value is definitely 0. So that was probably the trickiest part of this, that thinking, if you look at the graphs, the height of the PDF is very clearly different. But the height of the PDF is not the same thing as the probability it equals that value. You got me. So mean. Maybe, actually, no, I think I used a slightly different version of this question in later terms. But anyway, so that was definitely a challenging question, and it was one that people did get tricked by. But yeah, that there is a difference between the probability that x equals x. That is not the same thing as little f of x for a continuous random variable. For discrete random variables, that is true. That's literally the definition. But these here are continuous random variables, and so it's not true. I noticed someone else say, can you make any meaningful statements about the variance of y from these graphs? That's a great question. Not really. Nothing that we would be able to tell you, it's hard. Also, it looks like this tail might kind of go off to infinity. It's hard to tell from the graph, but it looks like it might actually just keep going. And so that makes it very difficult to tell whether that variance is bounded by anything in particular. So I don't think we could ask you anything like that. Just looking at a generic graph, what is true about the variance. What we could do though is compare two different graphs and say which one looks like it has a larger variance or something like that. Because again, the more spread out it is, the more dispersed or whatever, the larger the variance is going to be. So the numerical value of the variance is sometimes hard to tell. You could put a bound on it again if the range of your random variable is very clearly bounded, but it's hard to tell just from looking at it, a single graph without any other context. So thanks for asking that. It's hard to say anything specific about it. All right, thank you for asking that question. Hopefully this kind of gave you a little bit of a review of some of the things we can do with continuous random variables as well, in terms of telling means and variances and what we can learn from the PDF. Also, why is C of part B discrete, uniform, but not geometric? Okay, yes, I will do that one as well. So it says an instructor has n identical looking keys and only one of them opens the door. She draws a key from her knapsack and tries to open her office door. If the key does not work, she draws another key. So she's not going to repeat. Not going to put it back in and shuffle them up again. It's definitely a different key. And continues the process until she obtains the correct key. And X is going to be the draw on which she obtains the correct key, where the draws are numbered 1, 2, 3, etc. So the question is, why is this a discrete uniform and not a geometric? And the key is, worst pun ever. I'm sorry, I didn't even mean to do that. Now I can't think of any other word. The most important idea of this one is that the instructor in this example is not putting the keys back in and shaking them up again. If that was the case, if the draws were with replacement, then it would be geometric. Actually, it would be geometric plus 1, because the key on which you get the trial on which you get the success is the geometric is the number of fails, and then the very next one is the success. So I'll just try to write drawing keys one at a time. Which draw is success. So again, if the draws were under the same conditions with replacement, then it would be geometric. But it says that she tries another key, a different key. So if the key does not work, she draws another key, as in she doesn't like put it back in and shake them up and then have a chance of getting the same one again. And in that case, we could think about, okay, what's the probability she gets it right on the very first try? So since it's without a replacement, the probability that like x equals 1 is 1 over, how many keys? N keys? Or is it k? N keys. That's pretty obvious. But the probability x is equal to 2, that means you had to get it wrong on the first try and right on the second try. So wrong on the first try has probability n minus 1 over n, and then that key is now out, disqualified, not going to be used. And then the probability that you get it right on the next try is 1 over n minus 1, because there's only n minus 1 keys left in the knapsack. And so that is equal to 1 over n. And then similarly, for all other values of x from 1 up to n, then the probability is 1 over n. So we end up with a discrete uniform on 1 comma n for that problem. So thanks for asking. Yeah, I noticed, I understood the question wrong, thought it was with replacement. Yeah, we would have to say something like, then returns the key to the knapsack and shakes it up, or independently, or something like that. So same idea with like choosing, try to guess passwords or something. Like if you're trying to guess passwords and you never guess the same password twice, then the probability of, then the distribution of the trial on which you get the right password is going to be a discrete uniform with a really, really large range if it's a secure password. Or like drawing cards from a deck one at a time. If you're drawing cards from a deck one at a time without replacement, looking for the ace of spades, the draw on which you get the ace of spades is discrete uniform on 1 to 52. Something same. They're all the same problem, basically, just drawing one at a time from a sample. I saw another question. Can we do a transformation of random variables question? I don't have a specific one. I don't know if it's hard to make one up. I can make one up. How hard can it be? It might be a disaster, but I think hopefully it'll be okay. Transformation. I assume you mean like a continuous one, because we don't really talk about it much in the discrete case. But so let me know if that's wrong. Okay, let me see if I can think of a good example that won't be too easy, so easy to be useless, but also won't be so complicated that we get messed up. Okay, let's say x has, sorry, my grammar is terrible. Let x have PDF little f of x equals 2x cubed. No. 3x squared. That's what I tried to say and failed. For 0 less than x less than 1. Oh, sorry, that you can't see that. For 0 less than x less than 1. And y equal, let's go 1 over root 2x. Just try and make it super complicated. Find the PDF of y. If this question is actually somewhere, if this is actually on the final, I can't, I mean, the chance of that is I literally pulled this out of my brain. I hope it's not anywhere, but if it is, good luck. All right, so that's what we're going to do. So remember, we want this 3-step process for finding, for doing a transformation. And I always recommend, like, usually I'm like, you can do it by intuition if you have an intuition, but for transformations of random variables, it's so tricky to know when your intuition is right and when it's wrong that I always recommend just follow the 3-step process for this. So step 1, we write the we write the CDF of y in terms of the CDF of x. So big F sub y of y is the probability that y is less than or equal to little y. Well, sub in the definition, that's the probability that 1 over root 2x is less than or equal to little y. And then we're going to try to isolate for x. So we're going to take the reciprocal of both sides. We're taking here, x is already positive to begin with, and we're taking the positive square root, so we don't need to worry about negatives. So this is the probability that root 2x is greater than or equal to 1 over y. Again, because when we take the reciprocal, we flop the inequality sign. Then we're going to square both sides. And remember, we have to be careful, right? If you square both sides, are we taking like absolute values here? In this case, x was positive to begin with, so we don't have to worry about anything like that, but it's always good to think about it. So this is the probability that 2x is greater than or equal to 1 over y squared, squaring both sides. And then we'll divide both sides by 2. Okay, probability that x is greater than or equal to 1 over 2y squared. Does that look right to me? I think so. So our goal though was to write big F of y in terms of big F of x. We haven't quite done that yet. Probability x is greater than or equal to something is just 1 minus big F sub x of 1 over 2y squared. So we've done step 1. We have written the CDF of y in terms of the CDF of x. It's a pretty messy looking expression, but we've done it. Step 2, we want to, in one order or the other, sub in the information we know about f of x and then differentiate to get the PDF. So we can do it in either order though. Let's try it one way. Let's find big F of x, right? We need that to be able to evaluate this expression. So this is going to be the integral from 0, the bottom of the range, up to x of little f of u du. But that was, what was it? 3x squared. 3u squared du. And integrating that, we'll get 3u cubed over 3 evaluated at 0 and x, which is x cubed. So the CDF of x is just x cubed if x is between 0 and 1. And if we really want to be fancy about it, it's also 0 for x less than 0 and 1 for x greater than 1. So that's our CDF. Okay, so that's cool. So now we can use this to find big F of y. So big F sub y of y, it's 1 minus big F sub x evaluated at 1 over 2y squared. And so that's 1 minus that whole thing squared. So whatever that argument is, we're gonna cube that whole thing. So it's 1 over 8y to the 6th. Oh my goodness, I'm sorry, this is a disaster. Okay, yeah, 1 over 2y squared. We take that whole thing and cube it, and we'll get 1 minus, 1 over 8y to the 6th. Okay, cool, great. But that's not done because we wanted the PDF of y, not the CDF. So we can say little f sub y of y is going to be big F of y prime. So it's going to be the derivative of this. And so the derivative of this, the derivative of 1 is nothing, and the derivative of 1 over 8 of negative 1 over 8y to the 6th, that's 1 over 8y to the negative 6. So the negative from the negative 6 will cancel out, and then we'll get 1 over 8y to the 7th. Just differentiating with respect to y. So you should be able to get that without too much trouble. There was not a lot of complicated integration happening here, but that's what you should get. So that's our probability density function of y. And then step 3 is to find the range of y. So x is between 0 and 1. So y, which is the square root of 2x, I believe. Let me double check. Oh, 1 over the square root. of 2x. Let me fix that then. Is going to be between, well, if x is towards the smallest possible values, 0, then this is going to balloon to infinity. It's just not going to have it's not going to have any maximum. And if x is getting really large, as big as it can get, if it's getting all the way up to 1, then y is going to be 1 over root 2. So we'll have 1 over root 2 and infinity, I guess. So that's not a very formal way of writing it, but you could just add this for y greater than 1 over root 2. So this is our probability density function of y. Oh, did I mess up? It's possible that I integrated or differentiated wrong. Please fix my calculus. Calculus should be done in private, not in public. But that's kind of walking you through the process. So we write the CDF of y in terms of the CDF of x, then we sub in what we know about big F of x, and then differentiate to get the PDF if necessary, and then we can find the range. We could actually find the range first. There's nothing that means we need to leave it to last, but we could do it either way. I mentioned though that we could do step 2 in the other order. So I'm going to say like alternate step 2. We could say before we sub in, so like pretend we never found the CDF of x, because we don't actually really need it. We know that little f of y is d by dy of big Fy of y, which is d by dy of what we found, which is 1 minus big F sub x, evaluated at 1 over 2y squared. Close that. So we could write that as, well, d by dy of 1 is nothing, so that disappears. It could be d by dy of fx, so the derivative of fx of 1 over 2y squared with respect to the inside part. So that's going to be negative little f of x evaluated at 1 over root 2y squared. And then times, by the chain rule, the derivative of 1 over 2y squared with respect to y. So times 1 over 2 negative 1 over 2y cubed. That's what we could do, right? This is the chain rule. And then we could sub in, right? We know that the negative signs will cancel out here. That's going to cancel with that. And little f sub x evaluated at 1 over 2y squared, we had that little f was equal to, way at the start, 3x squared. So 3 times this thing squared. So yeah, when we differentiate here, we're not just multiplying -1, we're multiplying it by -6. So there should be a 6 up here. 6 over 8 y to the 7th. Yeah. Thank you very, very much. So that's going to fix the problem down here. So I'm glad I did it both ways, because I'll catch the mistake that I was going to make. So 3 times y squared. So 3 times this whole thing squared, 1 over 2y squared squared, and then times twice. I did the same mistake twice. So here it shouldn't be -1, it should be -2 here, and then that's a 2 as well, and then that is a 6. Okay, good. At least I'm consistent. I differentiate incorrectly the same way both times, because I was trying to go quickly. But there we go. So that's how you would do it in this way. And the cool thing about this way is that you don't need to find the CDF of x. We never needed it for this second way. We can just go straight to it. But it is a little bit more difficult because you have to sort of remember to differentiate using the chain rule, and it can result in some messed up things happening. But in either case, again, we would then find the range, and we would have 6 over 8y to the 7th as our PDF for y greater than 1 over root 2, there you go. Okay, so thank you for asking that question. Again, I apologize for my terrible calculus. Hopefully that the process made sense. When I try to make up an example, I hope that it works out nicely, and this one wasn't great, but at least we've gone through the process. So thanks for the question. Part 3, question 2A from the sample final. So part 3, question 2A. So I'll see what that is. Question 2A. Suppose that the lifetime of a certain brand of light bulb follows an exponential distribution with mean lifetime 1500 hours. So that means our theta is 1500. Light bulb lifetime is exponential with mean lifetime 1500 hours. And there's different classifications of quality. So if the lifetime of a bulb exceeds 4,000 hours, it's great. If it's between 2,000 and 4,000, it's good. If it's between 500 and 2,000, it's fair. And if it's less than 500, it's poor. And then we've got a box of 20 light bulbs, and then we're looking at what's the probability of a bunch of different things. So you immediately, looking at this question, you see that you've got a bunch of different categories, and light bulbs are independent. I'm pretty sure it mentions that. It doesn't actually say that, but sort of implied. And we're looking for like specific numbers of each type of outcome. So you know that this is a multinomial type question. But the probabilities, the P1, P2, P3, and P4 for the 4 categories are coming from an exponential distribution. So this is a question incorporating both the multinomial and the exponential. So the first thing that you need is the probability of those categories. We need the probability of a good, or a great, good, fair, and poor category. So let's say probability of great. That's the probability that this lifetime exceeds 4,000 hours. And for an exponential, we know that that's going to be 1 minus the CDF. So 1 minus e to the negative x over theta. So 4,000 over 1,500. And then you can cancel the ones easily enough. So just e to the negative 4 over 1.5, whatever that is. 6, e to the negative 6, whatever that is. Similarly, like the probability of good is the probability that x is between 2,000 and 4,000. And for any random variable, this is just the probability big F of 4,000 minus big F of 2,000. Right? The probability of x being between A and B is big F of B minus big F of A. And each of these is going to be similar to this expression up here. So altogether, we'll get like 1 minus 1 minus, so e to the negative 4,000 over 1,500. 1 minus that, minus 1 minus e to the negative 2,000 over 1,500. And so those 1 minuses will cancel out, and you'll just get e to the negative 2,000 over 1,500 minus e to the negative 4,000 over 1,500. And similarly for the other categories. So you could find the probability of fair and poor. Poor is just the probability x is less than 500, which is 1 minus e to the negative 500 over 1,500. And then fair is just 1 minus the other 3. However you like. You only need to calculate 3 of those 4 probabilities, and then the other one is the 1 minus the other 3. So hopefully that helps the person on Piazza. I'm going to just double check whether that was... Okay, great. Yeah. And then, once you have those categories, then you use multinomial. Because we've got 20 light bulbs in the box, so our n is 20, and we have these 4 categories, and then and that'll give us the answer to all of those problems. And then remembering, when you're working with the multinomial, pretty much everything that you're asking for, like more specific than just like exactly specifying what's happening, turns out to be a binomial. because you can sort of define a success to be whatever you like. Like if you're asking what's the probability that like a certain number of the bulbs are great or good, you can just define success to be great or good and fail to be anything else. Or if you're looking for like a single category, you just define that to be a success and then define everything else to be a failure. And then you have a binomial situation. So the binomial has lots of nice like shortcuts when we're looking at either conditional or marginal or like sums of variables within a multinomial setup. Okay, so now I'm going to do the other one, which is question 4 of part 3 from the sample final, which I believe was the indicator variable question, if I am not mistaken. Okay, question 4, yes. So 20 different types of collectible cards. That's the one that you wanted me to do. I will do it. Part 3, question 4. So we've got 20 different types of collectible cards. And each time it's equally likely to be any of the 20. And X is the number of types of cards you still do not have after buying 10 random cards. So that was supposed to be a Y. You buy 10. And X equals the number of types you do not have. And then find the mean. Oh, sorry. My face is in the way again. There we go. X is the number of types you do not have, and we want the mean and variance of X. And it's given you a hint to use indicator variables, basically. So the way this question is worded, or set up rather, is this big blank page. It's kind of intimidating to just like have a question and like a huge blank space. I've gotten better at writing questions since I wrote that one. That was literally the first time I ever taught Stat 230 a long time ago, and I wrote that question. So now I'm much more likely to break it down for you to sort of say like, all right, first find E of x1, and then tell me what E of x is, and then find variance of x1, and then find the covariances, and then tell me what the variance of x is. So now I usually give you a bit more guidance than just sort of like a huge question worth 10 marks with no guidance, no steps in between, just in case that was making you nervous, that it was like so much to figure out. But the process for doing indicator variable questions is almost always the same. I did do a little review in the last live stream of like the basics of indicator variables, so I'm not going to do that again. I'll just do this question. But if you struggle with indicator variables, I suggest going to watch that as well, just because it gives you a pretty good idea of like how we can work with them. But let's go for this question. So we're going to start off by defining xi to be 1 if you still do not have card type I. So if no type I's, and 0 if you have at least 1. And so what you need is to find the expected value of xi. We just need the probability of that happening. Because it's an indicator variable, this is just the probability that there's no type I cards chosen or purchased. And if we're buying 10 cards, and each card has like a 1 in 20 probability of happening, then this is now just kind of like a counting problem. So if we have type I, if we want to exclude type I from consideration, then there's 19 out of 20 other possible choices. And so we just have 19 out of 20 on each of the 10 choices. So every time we're buying a card, we have to not get type I. It says nothing about other types, right? Like when we're looking at indicator variables, we're just looking like laser focused on this one event. Like what is the probability that we don't get any type I's? For that to happen, all of the 10 cards we select have to be from the 19 other types. We don't care how many of each, but we end up with this here. So that gives us our expected value. And as a bonus, that instantly gives us the variance of each xi. Because for indicator variables, the variance is just the probability that the associated event is true times 1 minus the probability that the associated event is true. So that's just for free. as soon as we find the probability of the associated event with that indicator variable, we instantly have the mean and the variance. The last thing we're going to need is the covariance of xi and xj. And again, depending on the problem, there might be situations where all of the covariance pairs are equal to each other. That was the case in the like hats or like letters into envelopes example. That was the case in the like hypergeometric example, and that is the case here. But there's plenty of problems where the covariances are not always equal. So in the course notes, there's one where there's like things that are stuck together by like little tags and a machine is cutting them. So the ones on the end have different pairs of covariances, different variances for the ones on the end and different expected values. But also, if two things are connected, they'll have some relationship. But if, we're talking about this one over here and that one over there, and they're not anywhere near each other, then there's no covariance. So there might be cases where the covariance is 0 for some pairs ij, but non-zero for other pairs ij. Another one in the course notes where there's like a necklace of 5 beads is kind of similar. And there's one where there's like 5 islands with bridges across them. So you just have to be careful. Sometimes the covariance is equal for all pairs ij, and sometimes it's not. And it's not always easy to tell, but you have to investigate and think about, okay, does it always have the same relationship, or is there like some adjacency thing going like that? Someone asked how do you do it when they're different? I'll come back to that. I'm going to finish this problem and then I'll come back to that. That's a great question. Okay, so here, for any pair ij, all we want to do is find the probability of both I and j equaling 1 at the same time, because that's how you find the expected value of xi, xj. And then again, minus e of xi times e of xj. Well, to have both of them not be gotten in 10 draws, that's going to be now 18 over 20 to the 10, because you can't have any i's and you can't have any j's. So there's only 18 choices for each card, and then we have to do that 10 times. And then minus, well, we already know what the expected value is. It's 19 out of 20 to the 10, and then 19 out of 20 to the 10. Okay, so finally, we are ready to put all the puzzle pieces together. E of x is just the expected value of the x, which is the sum of the xi's, which is going to be, because of linearity, the sum of the e of xi's. So it's the sum like this, as I goes from 1 to 20, which is going to be the sum as I goes from 1 to 20 of these e of xi's. And each of those we calculated, so altogether we'll have 20 times 19 over 20 to the 10. So that's our expected value. I don't care what the number is. You can calculate it if you like. And variance is going to be the sum of the variances plus 2 times the sum of the covariances. Again, that's one of the formulas from the rules, I think 9.5, rules for linear combinations of random variables. So the question is, we know there's 20 terms in this sum here, but how many terms are there in this sum? That's where the hint comes in. It says the number of pairs ij with I less than j is 20, choose 2. So I even gave that to you. That was my one olive branch, I guess. This was a tough question without any guidance. So 20, choose 2 terms. And so we can finally put this all together. So we'll have 20 times the variance, which we found was 19 over 20 to the 10, times 1 minus 19 over 20 to the 10, plus 2 times 20 choose 2, times the covariance, which was 18 over 20 to the 10, minus 19 over 20 to the 20, I guess, right? Just shoving those together. So that's a big mess, but you could calculate it, and that would give you hopefully the same answer that I got. So does that help the person who originally asked that question? Hopefully yes. And I do want to talk about then, how do you do it when they are different? So when the covariances are sometimes 0 and sometimes non-zero. I'll just add a little note here. What if covariances... Oh, someone asked, why do we raise it to the 10 again? Because we buy 10 cards, right? If it was one card, or if we only bought one card, we wouldn't need to do that. But we're buying 10 cards. So each time we buy a card, and we buy cards independently, it says that each time it's independently equally likely to be one of the 20 types. So if we want to get no type I's in 10 cards, we need to get no type I's the first time, and no type I's the second time, and no type I's the third time, etc. So we have to multiply 19 over 20 by itself 10 times because we're buying 10 cards. If we were buying 15 cards, it would be 15, like to the power of 15. Does that make sense? Again, it's kind of like a chapter 3 type problem almost, back, like casting our minds back that far. Cool, great, awesome. So yeah, I'm going to return to this idea of what if the covariances are not all equal? Again, the way you can tell is if there's some like physical relationship in space. Usually that's like kind of the way that you can tell. So I'm just going to borrow from one of the course notes questions, which I think was actually also on one of the Mobius quizzes. There's like a bunch of things connected like this. And a machine is going to come and cut them. So like a machine is going to come and like slice through these thingies, but sometimes it misses. So sometimes it doesn't get them. And so we sort of define an indicator variable for each thing as to whether or not it's fully separated from the ones around it. And so like x1 relates to this one, x2 relates to this one, etc. And like xn relates to this one, xn minus 1. So first of all, the means are slightly different, right? Because if x2 is completely separated, that needs 2 cuts. Same with x2 through xn minus 1. But x1 and xn only need 1 cut to be completely separated. So the means and variances of each individual each individual indicator variable are also not equal to each other. But that's okay. You just calculate it for the n bits and calculate it for the middle bits, and then you add 2 times the n bits plus the number of middle bits, and that's your expectation, because expectation is linear. But for the covariances, here we can see that, like, I guess, if this is x3, x1 and x2 are going to be related to each other, for example. Like, if we know that x2 is completely cut off, like completely free from the little connecty bits, then x1 for sure is also free. Or something in the middle. Like, if x2 is free, then it's pretty likely that x3 is also free. It might be or it might not be. But they share that little branch in the middle. Like, x1 and x2 share this branch here. x2 and x3 share this branch here. So there's going to be a covariance, a positive covariance, or sorry, not positive, but a non-negative, in this case positive, but in general, a non-negative, non-zero is what I meant, a non-zero covariance between x1 and x2, but between x1 and xk, like a random one, like xn minus 1, there's no relationship whatsoever. So like in this case, the covariance is going to equal 0 unless the variables are adjacent to each other. So like j equals I plus 1 or I minus 1. J equals I plus or minus 1. Because again, like whether x1, like whether this thingy here is cut has nothing at all to do with whether this thingy here is cut or this thingy here is cut. And so those are all independent. And so if we have 2 variables that are right next to each other, they might have something in common, and you would need to figure out that covariance, and it would be non-zero. But if they are not related to each other in any way, if they're not adjacent to each other, then the covariance is just equal to 0. And so you would do that, you would find the covariance for each of the pairs, and again, like it would be different, like for x1 and x2 and xn minus 1 and xn, it would be something. And then for any of the other pairs, it would be something else. So like 2 and 3, 3 and 4, 4 and 5, 5 and 6, etc., up to n minus 2 and n minus 1. And then when you're doing this part here, you just notice that like not all the terms are the same, right? Some of them are 0, some of them are this first thing you calculated, and some of them are the second thing that you calculated. So you just have to make sure you're adding up the right number of each of those covariance terms. So does that help? Again, there's a few problems like this. There's, again, the one that looks exactly like this. There's one with switches that are on or off, and then we're calculating the number of unlike pairs of switches, like off beside on or on beside off, that's going to have the same thing. Like a variable is only going to be related to the one adjacent to it. There's one about, again, the islands. There's like 5 islands and they're connected by bridges. That's another one where the covariance terms are not all equal. Some of them have a non-zero covariance and some of them have a zero covariance. So I would suggest try as many of those as you need to feel comfortable with this idea. But that's kind of the idea of how to approach a problem like this. Does that help? Oh, sorry, yes. So to summarize, I just sum the ones that are non-zero and ignore the ones that are zero. Yes, that is a great way to think about it. Yeah, just be like, if they're zero, doesn't matter. Just don't even include them. So you're just only focusing on the number, or on the ones that are non-zero, but just don't forget this 2 here. So it's 2 times the sum of all of the ones that are non-zero. Great. Okay. So I'm not seeing any new questions coming in. Thank you everyone so much for joining me. I hope you have a good night. If it's night where you are, I hope you have a good morning if it's morning where you are. I'm glad. Oh, thanks. You're very welcome. I'm glad it was helpful. There's also a couple of other review thingies that I've done in some of the live streams, especially about indicator variables in general, if you're curious about that. And good luck, everyone. Have a great weekend and good luck on the exam. Take care of yourselves, drink water, and I will see you at the exam. Well, I won't see you, but I will be with you in spirit at the exam, and I will be checking Piazza frequently. So best of luck. Have a good night.